We directly move on. The next presentation is being held by Dr. Stefan Klußmann. Dr. Stefan Klußmann is the CEO and co-founder of Planerio. And he's giving a speech on the shift planning with quantum computing, or how to create employer satisfaction fast. Stefan, the stage is yours.
Thank you very much. So excellent. Nice to be able to talk to you. So what you will be hearing in my presentation is probably a bit different from what you've heard in most other presentations, because we are a small company. So we are only 6 years old now. And our main focus is also not quantum computing and hardware, but we are a software company. So we're a young software startup in Munich with now a bit more than 70 employees that, as the name may indicate, Planerio deals with planning. So we are doing shift planning in the healthcare sector. So for hospitals, large practices, care providers, and everything that's connected to healthcare. And the problem that we are facing in our day-to-day life is manual shift plans. I mean, you can imagine, or well, you will probably be surprised at some stage how shift plans are done in a hospital. So more than 95% of the hospital use digital tools, namely called Excel, to calculate and, well, not calculate, but to generate the shift plans. And this faces a lot of problems. It is very manual, so it's time consuming and obviously takes a lot of energy of the planners, which are typically the doctors or leading medical technicians. It is, as you can imagine, prone to errors, and it's difficult to keep the overview of what's actually happening and which is the current and latest shift plan. There's a strong aspect of intransparency, how this process happens. Why did I get this shift? Why not the others? Why is it fair? So there's perceived unfairness in the topic. It is obviously time consuming, but it's not just about creating an initial plan, but it's also to work with the plans and adjust it if somebody gets sick, if there's requirements that come in, and so on. And what most of the owners of our customers think about, how can I optimize this? Personnel accounts for 60, 70, 80% of my cost. And I have so little personnel and I see inefficiency in the plannings, and I cannot get a handle on optimizing that. And this is where Planerio comes into play. At Planerio, we say in German, verzetteln war gestern. So we're trying to get rid of all the paperwork that's connected to the shift planning. So we get all the things that you require to do shift planning into our tool. That is obviously regulatory requirements, that is the locations, the employees, the qualifications, the wishes, the vacations, and so on. And then we have our AI-based algorithm that calculates the shift plan. We always say it calculates the best shift plan, but this is what we're using is a genetic algorithm. So you can imagine that obviously it is a very good shift plan, but technically it's not the optimal one. So in the middle of our work, we always describe this algorithm as the brain, let's call it like that. And then what we do is, and what we help our customers with, is to do the resource planning of the allocation of employees to the shifts in a, let's call it, cross-location manner. So we try to help our customers to get away from small shift groups of 5 or 10 or 20 or 30 people towards larger shift groups where you can really gain efficiencies. We have the employee app, obviously, that the employees interact with the app. We started out with planning, but we realized quickly that actually our customers also need time management. So time tracking and time management. They also need payroll preparation, because obviously if you work a certain time, get a certain bonus on a shift, this needs to translate into the payroll. And we are as a cloud-based company, a SaaS software as a service company, and obviously data security and privacy is very important to us. When we do automated shift planning, we start out in general with an empty shift plan. So we take up the shift plan pattern from our customers, working together with them. For example, that they have each day 2 early shifts, 2 late shifts, and 2 night shifts. And it started with this being empty. And then these shifts are connected with qualifications and other, obviously, rest times and everything that's required by law, TVÖD, Tarifverträge, and so on. And then essentially our genetic algorithm starts and assigns employees to these shifts. And as a genetic algorithm works, obviously there's a lot of variables that this one needs to take into account. So there's a target function against which this is evaluated. Then obviously the plans are calculated and computed. They are evaluated against the target function in terms of a fitness function. And then there's going to be mutations. And then there's the next selection round, mutation, selection, mutations. And this can be done hundreds of times with millions or more, multiple millions, even billions of shift plans calculated in each cycle of creating the optimal shift plan for a certain customer. And a major problem that we are facing is that what is the optimal shift plan? This strongly differs between each customer. So some customers, for them, it's horribly important that the night shifts on the Sunday and Saturday are distributed equally because there's a certain very strong bonus attached to that. Others say, well, our target objective is to get our working hours to the 30 or to the 40 or to the 25.5 hours. So for each employee, this needs to be important. And there's always these combinations of all these, in the end, constraints, some hard, some soft, that you need to overlay and get together. So we realized that, well, the automatic planning is a nice thing and really helps our customers. And in general, we see that the calculated shift plans, after we adjusted it to the customer needs, are significantly better than what the customers did before. And it's some work to adjust it, yes, of course, but it has significant advantages. It saves a lot of time. It increases happiness, transparency, and so on. And what is very important to our customers, or to many of our customers, is that it allows different degrees of freedom in planning. For example, we have a large customer, a Munich-based radiology practice. It's not the practice next door that has like 2 physicians and 10 employees overall, but they have more than 300 employees at 16 locations. And what they did, they had 7 different planning locations, and they fused all these planning locations into a single large planning schedule, and in order to then calculate better, higher quality shift plans. So they saved on the time that was invested in orchestrating the shift plan. So from 6.5 people, they went down to 1.5. So they actually had more time that they could spend with the customer. And they also increased the quality. But there's a problem, obviously. There's a challenge. So we're getting towards a challenge that the larger the shift groups get, the more our genetic algorithm comes into a situation that it does not find optimality. As you can imagine, a shift plan, there's a lot of potential options. For example, if you have a shift plan with only 5 employees, so a very small one and 25 shifts, so essentially a week's of a shift plan, there's already almost 25 billion potential combinations. So it's difficult to evaluate in a deterministic fashion. And we realize that the larger our shift groups get, and that strongly is the trend with our customers to fuse shift groups towards getting more degrees of freedom, essentially, in planning and distributing people, making the plan better for them. And but we find that our genetic algorithms can or will get at some stage stuck in local optima. And if we want to get beyond that, we come to the problem that we cannot calculate the shift plans in times that are nicely acceptable to customers, because if it takes 3 hours to calculate a shift plan, or even 24 or 3 days, this is not accepted by our customers anymore. So we were looking for options how to get to good or optimal shift plans faster. And this was a situation in which we kind of stumbled across quantum computers, because the shift planning is an NP hard problem, and that clearly, if it can be solved, would be able to be solved fast on quantum computers. And we were lucky because, as I said in the beginning, as a small company, we don't have the capabilities to do quantum computing ourselves. Neither do we have the budget to do so. We had the opportunity to become part of the PLANK or PLANK UK project. That is a government-funded research project in order to apply quantum computing to a variety of different real-life, let's say, business challenges. And we are applying it to calculating shift plans in high quality very much faster. And we used the care sector at first as a first example, and we'll get into the results quickly. So I don't know, many of you or some of you may have heard of the Planck project, but I think it's a really, really interesting and great approach because it aims at building a platform for quantum-assisted artificial intelligence. So the objective is to make quantum computing easily accessible to users, and not just to the large companies that have the budget and the willingness to do so, but also to smaller customers or those customers that maybe kind of the German Mittelstand, as always said, that could benefit from quantum computing, but just don't have the capabilities internally. So the Planck project consists of 19 different partners from industry, research, so it's large companies and startups like we, and that are working together towards investing and investigating the possibilities of quantum computing. And in this respect, many thanks to all of our collaborators, because obviously we don't have those capabilities to do everything for ourselves, but we're working nicely together with the QAR lab of the LMU Munich, Professor Linus Popien and Dr. Gabor, that are helping us evaluate different approaches, how we can apply quantum computing to our scheduling problem. And we started out trying the straightforward and simple thing. So here you can see a result from using our genetic algorithm on a very small plant. So this is a very small artificial plant that you will not see in real life, but it's a good starting point. So you can see on the left side, 2 employees, Diederich and Fassbinder, and 1 vacant spot. So in this line of vacant, all the shifts are going to be distributed to that the computer couldn't assign. And you can see different shift types in this calendar. So in this case, the blue ones are an early shift and the gray ones are the late shift. So as a first approach, we applied a cube approach, so quadratic unconstrained binary optimization to this problem. And this solves an optimization problem with the quadratic objectives without constraints and, well, binary variables. Since we have let's say, the challenge of not being able to specify the constraints, we need to add them as a substitute penalty term in terms of slack variables to the target function. So there's some trouble, some limitations, but also some benefits from that. And the QUBOs are a standard problem for quantum computing, and therefore we have the opportunity or the advantage of having available a large variety of solvency libraries. And when we, together with our collaboration partners, did that, we found out that actually small shift plans can be solved reasonably well with quantum computing, with a QUBO approach in quantum computing. And here on the right side, you can see such an example. So you already see that there's some patterns, but there's also some imperfections. Yes, that's because we didn't invest those 6 years as we did for our genetic algorithm into this one. But we clearly were able to provide the proof of concept that it works. But if we come to more complex shift plans, and those are actually the shift plans that we see in real life, we up to now with our approach failed to provide good solutions that are nearly applicable. So our collaboration partners did some research and suggested to do kind of different, more hybrid approaches. So here on the left side, you can see another shift plan calculated for larger, more realistic setup with 8 employees and a bit more than 100 shifts. And we used our genetic algorithms. And on the left side, again, those 8 employees and the vacant spots, and the color codes indicate the light blue is an early shift, the dark blue is a late shift, and the gray bar essentially is a night shift. And when we applied this Quagga approach, quantum-assisted genetic algorithm approach, we were able to get 2 plans. These are pretty fresh results, so it's not optimized yet, but we're confident that if we optimize this approach, we will get to reasonably well solutions already on samples that are getting close to reality. So the Quagga approach essentially performs the same steps as the classic genetic algorithms, but it uses the quantum computing. And then essentially the selection and recombination are still executed in the classical way. So only quantum computing for mutations. So that's the approach, because we knew that we get stuck in local minima. In this way, we have the way of navigating around that. So you know that the cube approach is an unstructured global search, and the Quagga approach essentially starts with a valid plan, namely placed by our genetic algorithms, and then goes and dives in and locally refines that. And we were now able to push the boundaries a bit further. So adding more shifts, adding more variables, more qualifications, some more constraints of different types, and increasing more shifts. So we're looking forward to seeing more than that. But right now we're still clearly in limitations. So what is our conclusion? So yes, we see that for small test examples, we're able to already now calculate good results within milliseconds. So there is a clear perspective that quantum computing can get a lot of benefit for us, but for larger shift plans, so for realistic setups, that also applies to other partners of the Planck project, essentially observes that the hard constraints are getting violated and that the results are not usable, not reliable anymore. So if we estimate for, let's say, a regular shift plan, we would have to have a quantum computer with around 16,000 qubits, ideally more, of course. We come to the direct conclusion that there's more investment essentially in developing these computers required. And if we see the whole development continued over the past years, then it is foreseeable that maybe in 5 years, maybe in 10 years, we can come to the stage essentially that quantum computing can actually be used in real life for solving the very complex shift plan problems. However, we're not there that we give up yet, because we see that the Quagga approach, this hybrid approach, already gives us some more freedom and leeway, because if we really achieve our objectives that we can calculate good shift plans for larger setups in seconds or milliseconds even, then there's a whole different possibility that open up. We can do forecasting very much more easily. We can do a lot of stuff in the future. So we will continue to invest on determining in how far we can live and optimize and go with hybrid approaches, and essentially cutting our large piece in which the Q was unable to really help us right now into smaller pieces that hopefully in more short term can be solved by quantum computers. Thank you very much.
Thanks a lot for the presentation. Maybe one question as a follow-up. How does you described in detail the research project you are doing, and very interesting the insights of your considerations in this context. How do customers react when you describe your plans and your future next steps?
Well, we have some use case customers in the setup from the care sector, because obviously it's always important to discuss with customers, and they clearly see the benefit of immediate plans. I mean, if you imagine that the plan of a care facility is not done by a mathematician, but it is done by a senior MTA. So we don't have to find the perfect plan and the optimal plan, but already good plans can be reached within kind of feasible amount of time. So what they see, yes, they see a clear benefit in the objectives that we want to achieve, namely quickly calculating plans. However, they cannot connect anything with quantum computing. Because quantum computing obviously is something that's somewhere in the air and the sky. They heard about it, but it's not now.
Okay, they are convinced by solutions, therefore. It's not about technology for them, it's about the solution.
Exactly. They want to see results. If you can show results, then they will think about it. Otherwise, they don't care. The users, they have a problem, they want to have it solved. How you solve it, it doesn't matter.
Thank you. There's another question from the chat, and it's regarding it's addressed to the quantum hardware you were using. So the question is, on which quantum hardware have you been able to push Quagga to 7 employees and 252 shifts?
So we used, I think, the D-Wave quantum computers. which exactly I would need to find out what the team used.
Yeah, but this is already very helpful. Thank you.
I think they used this D-Wave Advantage. I'm not 100% sure. This is quite good already as far as I heard.
I think this is already very helpful that you used the technology stack from D-Wave. Thank you.